it's fun.
See our culture as well. Yes, let's go
You want
ahead.
to
Yeah,
jump
yeah,
in here,
no,
Sergey?
it's thanks.
All right. Well, happy Friday, everyone. I know we are nearing the end of the term, so I tried to find a topic that might be a little more interesting for people who are odd sort of applications in the world of paper coming out of MIT, Caltech, and I think Northeastern was the last author, but they came out with this paper called KANs or called Magarov Arnold become very uh, interesting to say the least within the field of machine learning as potentially an alternative that they are building up their networks. But today, I hope to go through sort of this paper, a little bit of the dissent that the community has gone through, some applications, maybe better general understanding, but very loose presentation. Please feel free to unmute or just raise your hand or whatever. I have cameras in the corner, so I can hopefully see that. Sergey did note the talking dissonance between the multiplex. Today, this is going to be more the overview. Uh, the first author put in their paper. To be note, this is on archive rather than published in a normal journal. However, there is so much discourse on Hugging Face and Twitter itself that the author has updated the paper several times to include new findings from people from Twitter, from different universities for empirical results. But let's go ahead and jump into this. For a little bit of background, this is a theorem. The theorem did come out in 1956-57 when the initial papers first came out with several different follow-ups throughout the years. This is the bread and butter of most all machine learning, where we have. Are you able to see my pointer, or do I need to?
Yeah, we can.
Is my mouse okay? Yeah. So universal approximation function. We have our inputs, outputs, and this is the formulation for a shallow network. Here we have our fixed activation functions within the nodes, where we have learnable weights for the edges. Here we have the MLP is composed of this formula as we get thicker and deeper. We have nonlinear and there's linear fixed functions, but hopefully this is very easy for people in very much background. So this comes from the Google talk that uh, Zhang Li at a Google talk about 4 months ago, where they were saying that the universal approximation theorem is the foundation and the linchpin, more or less, for today's AI. Is there alternatives, especially as we're starting to get into scaling issues? We're starting to get to computational issues, energy issues. Can we find better fundamental building blocks? And so, what they are saying is back in 56, 57, we were using this alternative method that I'll get into uh, soon, but they wanted to see if the Ka representation theorem might be a better place for the universal approximation theorem. What came out in the late 80s here see uh, um, inclined to say that uh, these non-smooth functions will make sort of this new approximation fail because we are using quite a lot of 1D linear approximations that are combined together. However, why do we care now? It's 2024. What has happened? Why did Z and Liu decide to use this instead of something else? Well, these were his reasons, and specifically taken from his presentation as well. They doesn't care about exact representations, especially if we're trying to find models. A common occurrence in deep learning is if it's not working, or we need to do better representation, let's go deeper. And so it's a very hamstrung way of approaching it. But then he gets very cheeky and says, the can do spirit, let's just see how it works. And so that's where this paper ended up coming to fruition, where he is going to compare the multi-layer perceptrons with KNNs, specifically with deeper layered KAMs. As we know, we have the activation function where we have our inputs with the weights. They get summarized to some kind of function that has some initial bias. These get taken with an activation function for the Y prediction. We have a family of widely used activation functions that have a myriad of empirical results and very specific use cases, for example. But specifically, these are fixed, and activation functions are predefined in nonlinear. We know that the connections between the MLPs carry simple weights, and they're adjusted during training. KNs, for example, will instead of using fixed activation functions, we want learnable activation functions on the edges themselves. And I'll show you that here in a second. These are going to be constructed using basis functions like B-splines. And by using that, we can achieve highly flexible and expressible functions during learning on each connection. And they are all being replaced by coefficients within the edges activation function. So what does that mean? KANs, we have this function f, where we are going to have all of our inputs x. These are going to be modeled based off of some kind of phi function or single dimension function that will be approximated by phi. This gets summarized into this chain where we have this summation here. We can decompose that to a specific matrix where we have each of these phi functions that will be represented by splines and multiplied by our input features. So we have a combination of linear interpretable functions here. Yes.
Yeah. So you kind of jumped quick through this Tommaso Poggio and Giosi. But stay on the slide, please, because of the number one, right? So original statement, why Kolmogorov and Arnold, his student, who I heard did all the work, were working on this because of one of the Hilbert's problems, right? The Hilbert problem can any multivariate function be represented as a summation and application of univariate functions, and they proved that yes, it can. So basically, their proof is universal in that sense. Any multivariate function can be represented as a summation of univariate functions, like this application. 2 layers twice is enough. That's it. This equation number one was what they proved. And then I haven't heard about the result that you showed. Basically the result of Poggio, or not the result, but is not about this theorem is incorrect. The previous one.
Yes.
Previous slide.
This one?
Actually, yeah, non-smooth. Yeah, this one and the non-smooth part. So they're just saying the theorem is true, but in order to reconstruct any multivariate function, sometimes those inner univariate functions are non-smooth, right? Or cannot be made. Oh, okay. I didn't know about that result. That doesn't invalidate the universality or anything, right? It just says constructing this function may not match to what we're actually doing with deep learning, right?
Correct. Yeah, especially because what we assume as this five function being splines that it is continuous and differentiable, so we can do backprop on it. This does pose challenges when the underlying distribution is not necessarily differentiable or continuous.
Oh, that's interesting. Another result I heard this week is I mean, it's probably all the result. So we know that there is a theorem that proves that recurrent neural networks are Turing complete, but we don't know that the way we use recurrent neural networks are in completely orthogonal regime when what we do is never can make them Turing complete. It's kind of like this contrived settings. They are Turing complete, but the way we train them, the way we operate on them, we are not in the regime of their Turing completeness anyways. So.
Yeah, because I was also looking into state space models as well. I think S4 was one of the big one in Mamba was another one. A completely different paradigm to this that it was trying to get away from the universal function approximation by using more state space and then recurrency on top of that. That has a lot of its own issues and completely different than what this is. But I do agree with you. They're trying to get away from potentially needing to have this non-smooth factor into play here. I don't know if that makes
Great.
sense. I would,
Yeah, I just wanted to connect the dots back to Hilbert. It's not that
yes,
there is a continuity of the research of field mathematics.
yes. Great. So with that being said, let's jump into a little more of the KANs. Let's jump into what sort of B-splines are. Hopefully, you've all seen this in your I don't know which class you would have at Georgia State, but B-splines are really fun approximators. They are polynomial estimate based off of combined saddle points that are then used to estimate a function over input output. Here we can see a very basic example I pulled from a YouTube video. I didn't quite find an animation, I apologize, but each of these points, you can decide how granular or coarse you can make your spline approximation, and they do hold a very important fact of locality, whereas if you do move one point up and down, it does not drastically change the whole rest of the function. So, for example, if I had taken this green point and moved it up and down based off of these parameters, it wouldn't change the shape of the overall graph egregiously. There will be some changes, of course, but this is one of the more the localized property or the local conservation of approximation is what makes this very special for interpretation. Now, why is that important? Because we can be accurate and interpretable. I will get further into this, but this is one of the main advantages of using cons at the moment instead of a fully connected MLP. That being said, I'll go through more of what the limits are for this and sort of how interpretability goes through. So for accuracy, this was done by using toy problems. It was done using specific special case problems. They used the Feynman equations, and I believe they used fractal equation or fractal analysis as well. Some of this is outside the scope that I want to get into and a little challenging to understand sort of the toy results. But to give you an example of what they might be trying to interpret, they'll set up a multi-layer perceptron, and they will set up a KAN, and they will try to approximate the function f of y of x equals x times y. So just a multiplication factor, can they get that via the number of parameters, and then they have their test RS or RMSE. And so they have the theoretical limit here. What you will notice is that KANs, they'll have a depth of 2, where the MLPs, they'll have depths of 2, 3, 4, 5, where they're showing that there's some theoretical limit for the MLPs and there's a theoretical limit for the KANs. The test accuracy does decrease very quickly especially by using less parameters. Um, However, one thing to note as when you get to more complicated expressions, such as a multi-sign expression with an exponent in here, you're going to find that there are going to be a trade-off between the number of parameters versus how much that you need. So it's still very much a fine tune. Um, Question, I just heard a ping.
That's certainly I was trying to ask a question. Make a point.
Yeah, I was trying to add things. I was trying to. Okay, so the raising hand works. Not just the accuracy, and what was the second part? It's not just about that. Those plots also show something called parameter efficiency, which is important.
Yeah, with another a slide here. Specifically with B-spline, since we can choose how coarse or granule the number of estimates are for each of the function approximators, we can actually downscale it first and then make the model more accurate by making it more coarse. So it's a type of overfitting, but this way, I'll show you the benefits of this in a future slide, as this does have importance to empirical results. But going here, we have a comparability of special functions. I'm not quite sure the exact underlying functions that they have here. I believe they go into special functions in terms of solving certain PDEs and whatnot. But Pavel,
Yeah,
did you?
correct.
Yeah,
So this is more of a maybe deep than you wanted to go into at this point, but does it matter how they initialize the B splines for the activations? That's something I was always curious about. Like, how do they do that? How sensitive is it to that initialization?
It's one of the most outstanding questions that they have. This is in their I jumped ahead here, but this is in their supplemental part of the paper, but it is very specific to even the random seed that they choose. So even when you're trying to interpret specific nodes or inputs for the estimated output, you're going to have a variety of different effects to it. So this is still a very much open question and needs to be thoroughly studied.
That makes sense.
Yeah. So yeah, you're going to have some luck with certain random seeds. My guess is that with many of these results, they were cherry picked since there's quite a lot of results. But yeah, I think it's a great question.
Does the interpretability kind of go out the window in an average over seeds? Like, do you get like because you can't really like how do you average both lines in any meaningful way? It's like I don't really know.
Yeah,
Like,
so they get so this is a great segue back to where I was. The interpretability that they talk about is used by sparsification, and specifically with their algorithm, they have sort of this L1 regularization and entropy loss. But here, that will allow them to take nodes that are important and not and for the underlying result, and so you can find that say these two nodes are going to be an amalgamation of these two inputs. And so you can see how the author claims that these seem to be more interpretable as you increase sparsification over time. So you can find out which nodes were more important in describing which inputs matter and which nodes matter, and then the activation functions themselves were learned. And so we can see that the combination here will result in a very specific node function. Does that make sense? So
It does. Yeah, kind of. One question about the activation functions, and this is really relevant to interpretability, but do they still see that very different nodes getting highlighted across different seeds?
um, yes and no. So they do have one toy example where interpretability was geared towards having 4 and 5 be dependent variables, and they were able to learn this task. They did not provide very much data of like what is what kind of data they were inputting here, but I think there was just random variables that were dependent of each other. What I don't know is how they initialize, because you're right, Brad. I think that's a very interesting question.
Yeah.
Yeah, very nice. So in terms of the interpretability, all of these are very toy problems so far that we've seen. They have the ability to look at the accuracy of symbolic formulation. So by then having these functions within the nodes, they can use these new functions to then have accuracy of the actual underlying function. So for example, to do a symbolic representation, they can take the initial black box approach, do the sparsification, prune down to what their activation functions were, get a set, set the exponents, and then do the affine transformation, where they have a very good approximation of the underlying symbolic representation. This has implications for various physics problems, Navier-Stokes, Lorentz equations. I believe they have potential applications for different types of you name it. There's so many PDEs that might have there. Because of this result, the author makes a gigundous claim, saying that they can now beat the curse of dimensionality. There is quite a lot of math and sort of, I want to say hand wavy, but at the end of the day, they're trying to demonstrate that if you keep your B-spline sparse, then gradually incorporate more granule approximations, you can beat the curse of dimensionality by fine-tuning those specific points rather than change the overall activation function with every change of data. And so let's say, for example, myself, Sergey, Brad, we all have different wants on Netflix. Just because I like to watch, let's say, RuPaul's Drag Race, and Brad likes to watch Top Gear, that won't change us based off of other dimensions that we have. Like I have long hair, Brad might have mediumly longer hair. Does that make sense? So for this reason, they're able to discern more of the independent variables within the approximation, which they then extend to knot theory, which I'm not sure how familiar everybody is here with knot theory, but it gets very complicated, and especially how you define various parameters and whatnot. But more or less, it's just trying to find ways of embedding a I believe it's two dimensions apart from each other. I'm not an expert. I will not claim to be an expert. This is something that I should look into further. Neither was the first author of this paper, so you're not alone in this. This was definitely from a co-author here. But sorry.
Yeah, I saw
Yes.
your book.
Yeah, I've got a book in your lab on knot theory. It is quite interesting if you're into topology and like other weird stuff. It's like, yeah, it's bizarre. It's one of the weirder mathematical subfields you can get into.
Are they trying to sigma shock us, or there is actually a need for knot theory here?
There
In
are
this,
some applications as far as I'm aware in physics.
no, here in this paper.
Oh, in this paper, I don't know what they do.
For knot theory, I don't need applications fun, I mean, by itself.
Yeah,
But okay.
So maybe I can help with that. The why or the so what of using the knot theory is the parameter count. They are orders of magnitude smaller than DeepMind's traditional MLP with this layer that was published, whereas the KAN with two layers only had a three order approximate, or basically 100 times less parameters with the same amount of accuracy. That's a pretty significant result. With that being said, there's a really fun result as well using PDE's examples. They show here that with different types of KANs versus the MLPs, they do converge quite faster with active loss and have a steeper scaling. That being said, there are some issues. This is a very contrived example that they also put in for sequential uses, where they try to say that the data, as you give more and more, they're trying to show that catastrophic forgetting happens with MLPs, as you would suspect, whereas KNs will learn over time. This is such a contrived example, and the author even says as much and says that this is just a foundational. But the reason why they put this here is they assume that LLMs are a type of language that need to be learned over time. Catastrophic forgetting does occur, and this might have potential use as a fundamental basis to avoid catastrophic forgetting sooner than using more regularization terms or more complex methods like LSTMs, GNUs, and et cetera, et cetera. So the big claims that this paper makes with those results is that it is 100 times more accurate, but with the added parameterization of the B-splines, it is 10 times slower. So what is the actual benefit of this? It's 10% efficiency. We can use around 10% less VRAM. Would this be a good use for LLM basis if we have to train for 6 months and use $1 billion to train it? I don't know. That's the big question that I think is the real crux of why everybody is interested in these basis functions. And so the question then becomes, well, then how do I use this? This was an example flowchart that the first author put at the end of their paper, using for accuracy, interpretability, efficiency, different types of variables that you would need within your research project. However, even the author in a tweet said that this is absolutely speculative work and used for future work. Like I kind of told you, like we went over earlier with Brad, it all depends on hyperparameters, the data that you have. Things get a little messy as you do. So this is the meme that starts to come around the internet when he started to come out. So it really is a means of playing around with this network. There still needs to be more theoretical limits put into the place, as most of these are empirical at this time, especially as we start to get community critique. We have the same results ran by 2 different people on Twitter, where we see that in the blue here we have the MLP prediction. We have some spline prediction ground truth with the green here. So we're looking at green for our ground truth, and then red is going to be KAN. Here on the left, we see that KANs are doing better, but over on the right, we see that MLPs are doing better, and I believe the differences is random seed and fine-tuning of parameters. The biggest critique of the paper that has come out, especially with Hugging Face forums and Reddit forums, is that the author did not train all of his MLPs to the extreme, and they did not get all the way trained properly, which resulted in kind of a mixed feeling for the community. Additionally, we can describe if we end up using ReLU as the activation function and just use it as the KNN, it just turns out to be just the MLP anyway, and so people are arguing that is it just overfitting, where we get this little bit where they add a little bit of noise and it goes, it becomes worse and worse, and the accuracy gets more smooth over time, and there's not really a way to better approximate this. Further, I found an example of someone just trying to fit noise straight up to the code that they have provided on GitHub, and they're able to produce 100% accuracy with just noise, and just do it with a random variable, and that's kind of concerning. And so basically, this is a great start to this research. It's hard to do at the moment. In one extension of this might be, well, why are we just doing the activation function in itself before and using this 1D approximation? Why don't we just learn the actual activation function? And this is a whole field in itself, beyond sort of what I have in scope of this presentation, but at the end in their appendix, they do go through learnable activation functions, which is essentially a MLP without a hard designation of ReLU or Xavier or anything of that nature, where instead they try to learn the activation function as well. This becomes computationally even more harder, and they make the claim that on synthetic examples, specifically these examples they show here are less interpretable than what I previously showed, and I can go back and forth if people want, but I tend to think it's just more noisy. But that's my opinion. I just wanted to put this here because I think he hid the uh, one of the more interesting findings, in my opinion. Little bit of a summary. Cans can get the best of MLPs and splines. Splines are great for low dimensional. We get local control, able to make sparser or coarser. We got some internal degrees of freedom. We are get back prop, great for computational efficiency, increase layers with to add complexity, and then external degrees of freedom. Big challenge. I think we've talked about the advantages here, but the big challenges are it's really slow to train and is currently not computational. One thing that they're saying is it runs slow because the activation cannot be batch computation, cannot leverage batch computation, so no GPU there. This is an engineering challenge that you said that there are people working on. So hopefully this isn't an issue as researchers continue to dive into this, or this first author starts to build this out. But challenges are scalability and really a lack of real world testing. Last thing, I didn't actually get to put it in this presentation, but I just wanted to show another more newer results. This was August 13th. Very incremental improvements. So this is for a field crop segmentation that I found. It's only 2% improvement over traditional models where it's using a UNet model to find better boundaries with crop field segmentation. Here they also try to explain that the UCAN predictions do better with their field or the field boundary rather than a gross conglomeration. But I need to look further into other applications. But I just wanted to throw that one out there just because I thought it was interesting.
I think I think Alex can speak to UCAN results. I don't think we found them that great. But Alex, can you comment?
So I think they kind of doesn't improve performance too much. Like I didn't see any big differences. To me, Umamba worked for some reason better than UCAN. But they all
Do you
use
think that was because it was the state space and it learned the representation faster?
It's very hard to compare because there are simple models that like UNet with residual connection is like strong baseline.
Mhm.
And if you go to MedNext that doesn't use any like new layers, it still performs as well. Umamba kind of was with a lot of parameters, but I'm not sure because of it. But I'll just say like they're not like drastically improving performance that like you would want to use them, I think.
Now,
And
is it just performance, or do you also get like a lower number of parameters significantly?
um, I probably can share some like plots. I have plots because without plots it's really hard to talk.
Sure.
But I think like you still want to try them and see whether they will help you. But just like I would be careful to claims because um, even now like we can use like simple like meshnet architecture and beat super like state-of-the-art results on the same data set.
Yeah, because I think one thing the author was trying to not shoehorn during a talk that I'd watched from them was they think this is going to be the universal function approximator for LLMs as it scales over time. And this is due to the fact that they can change the weights of the activation function without changing or having catastrophic forgetting in the long term, but there needs to be a lot more boundaries and empirical results to demonstrate this. I'm not sure how much truth that is, or if there's results that they're not showing for variety of reasons, or if they have computational resources that we don't have. But yeah, I'm just not sure about this method yet. Or mostly, I think the results were we should wait for 6 months so the big conglomerates can come out with their results about this for large language models.
I just think like it has like own place, and like I would just don't like trust anything. You just run it, like show your data. Like
Yes.
I think that will be the most important. But like like a lot of things that kind of like people develop or publish, like they can be very comparable, and in some cases they're better, and like you really have to understand why they're better. And
Mhm.
um, in the end of the day, I think most of the like for example, if you have like foundation models, they use like mostly same architectures, and like fancy things doesn't improve much. Like they can improve, for example, speed, like or long context. And I think we have to compare based on that. But overall, I think we also lacking kind of good hyperparameter research, and like different layers probably require different type of training. For example, like you might need like curriculum training, or
Mhm.
you need to apply different optimizers and so on. So a lot of the things are not like explored well with respect to hyperparameters. I think there is like probably small engineering is needed. Like actually maybe not even small, but I would just try them all if you want to kind of
Where
compare.
did it, TJ?
Yes.
I like.
What's up?
Where was it? Where was this paper published?
This paper was still on archive, but this specific paper was one of the reasons why people are dismissing KNNs so drastically, as they're even arguing that transformers are better than um, uh, the state space models, the state space approximators like S4 and Mamba. I can send this one in the chat as well. This is I didn't get a chance to go through this one, but they were arguing that number of training examples, number of characters in a string, different further examples, the accuracy goes down. So this is a whole nother bag of worms, but I did want to put this one out there that this is the specific paper coming from Harvard arguing that transformers are the best and we just need to stay with it.
Yeah. Okay. Yeah, I couldn't complain
Yeah.
if they got published without any big examples, because we've gotten rejected for lack of real world testing before, even though we did a ton of it. So it's just I always
I
complain.
think, yeah, I mean, this is a cheeky title. I don't know if this is actually published. This is just on archive. They're from Harvard, so they just might be cheeky.
I, I think I'm primarily interested in models, not only for the edge cases they might do better on, but because I think the analysis we can do with them is pretty interesting. In terms of learnable functions, I think that was something that really excited me for a long time when I was working on my low rank theory stuff. But
Mhm.
is that it's just a hard problem. Learning activation functions is you have to like bound them really weird ways. You have to do a lot of hacks to make them work. Uh, and like even the B-spline stuff, you have to do all these like weird hacks with like meshes, and I forget exactly what they do, but like it requires a
Yep.
lot of work. That makes then the theory extremely difficult. It's not as easy as just saying, okay, let's learn a polynomial function that like learn a Taylor series or whatever that approximates a good function. You can't do that because they blow
Yeah.
up.
I saw some extensions that instead of using B-splines as the basis function, they were using Chebyshev polynomials, where the bases are orthogonal to each other. That's its own can of worms, but you lose locality when you go fine grained to coarse as you approximate. So you lose some of the benefits of starting with sparser parameters. But I
Right.
think they have accuracy as you scale the parameters in the Chebyshev polynomials.
Yeah, well, I think those are
Um,
cool because we do analysis with them. But yeah, that's about the only like cool thing I've seen from these so far. Like they haven't had a lot of astronomical performance enhancement for how difficult they are to
I'm
train.
Yeah, because I guess I'm more curious is like how they do with higher, at least more noise within the data itself. I don't know, like frequency estimation or things that are kind of crazy with uh, big outlier events or like sparsity in events. I don't know because it seems like it's estimating more of a mean than I don't know. This is me not having to actually play with the code too, so I apologize. I didn't quite get to that this week, but this is more a summary of things that I found through the research.
Are you playing with code?
I've played with it a little bit. I didn't publish anything or get anything usable from it. Yeah, I was trying to do my low rank estimation and trying to do exactly that analysis where if you could learn an information function and know what that function is during training, can you exactly predict the rank? And I think you should for certain functions.
Mm-hmm.
It's hard.
That's interesting. Yeah, because I wonder. Yeah, because if you can see how much dependence there is with each variable, I wonder if you can. Yeah, that's an interesting question, Brad. Because I think that goes back to this guy right here.
All the other cool stuff like it'd be
Mm-hmm.
fascinating.
Yeah, new ideas.
Yeah.
But that is all that I have for today. I know we have, I don't know, what, 12 minutes left. Are there other questions? Is there things that are not clear about this or other results that people want to go over?
Other questions I've only.
Yeah. You don't have to like think hard and come up with something smart to ask, and just like whatever that is. I just have comments on interpretability, for example, while you're thinking. Because I think there's some kind of a category error here, right? So in transformers in those large language models, it maybe this mechanistic interpretability may not matter in the sense that yeah, hey, like you can understand how the transistors work in the CPU, but will you understand that we're playing AP3 of some kind of a Bach Beethoven symphony right now or not? I mean, it's totally at a different level, software versus hardware.
I think we need some levels of abstraction for
yeah.
This actually makes sense. I think that's a systematic problem with interpretability.
Yeah, so just a comment because this would be the mechanistic low level interpretability as it seems to me, not the sorry for using the E word, not the emergence kind of properties, but yeah, with this.
It's like during doing circuit analysis, but you only know whether each like part of the transistor is on or off, like exactly like you said, like you don't know the circuit, so it's only that level of information.
Yeah, like you don't know what's being executed, which kind of software, which kind of thing was being played.
I have a question. So this really reminds me of how CNNs were protected. Their internals. It's the same here, isn't it?
Sounds interesting, yeah.
But so then isn't this idea already tried in a very efficient way to be?
What do you think, TJ? The difference with kernels is that it's looking at one value at a time, right? That's kind of
You're trying to estimate function with kind of a root node. That's what CNN kernels are doing as well, right?
yeah. You're talking about the parson windows and well, the kernel density estimation in the sense that when you're smoothing the function estimate, that's how I interpret it. You're saying. But yeah, it's just another way to approximate functions, I guess, in a universal way, right? Going back to Hilbert's problem of can a multivariate function be approximated by or represented by univariate? The answer is yes, but we never used it practically. Plus, I know a different story, TJ. My story, but the old stories, of course, is that okay? There was Hilbert with this question. then Kolmogorov Arnold proved it non-constructively. And that yes, we can. And then people started thinking about constructive ways to prove it. How do we actually do it? And then they came up with the neural network universal approximation theorem. Your talk kind of puts them in the reverse order. So I think neural network universal function approximator comes from this as a result of people trying to think, how can we build it? And then I guess in 1989 they figured out, hey, those are different because this type of the kind type of approximation requires non-differential. Yeah, thank you. Not smooth base functions. But kernels is another way. I mean, it's all thinking about kernels is more like Gauss sum of weighted sum of Gaussians is a universal function approximation. So I would say this is the third way. I mean, they're all related, but
I guess it's a question of which universal function approximator is the best, right?
Like LLM, I mean, machine learning with like Fourier series. I haven't seen it. Does anyone know that? With Fourier series and frequency.
There's a lot of like wavelet CNNs and stuff. There's a lot of if you just Google like wavelet deep learning, you'll find a lot of stuff that's along that lines. That they, I don't know if it's quite what you're thinking, but like they learn in the frequency domain rather than in the whatever others like spatial or temporal domain. There's a lot of stuff that does that. That kind of learns the fixed form implicitly, or explicitly rather than implicitly, which is what we do with kids.
Wavelets seem to be more suited Fourier because the Fourier basis is infinite. And the wavelets here support this finite limited
But nothing outstanding that goes really well.
Not that I've seen. I mean, I haven't dove deep into that work. I mean, everyone claims that their method pushes the field forward, so it's kind of tough to weed out what's actually groundbreaking and what's not. I haven't seen anything that really stood out to me. But I think if there's some stuff for like time series analysis and stuff that's come out, it's there's probably 100 different papers, like wavelet CNN, or wavelet deep learning, like other stuff.
Any other thoughts, comments?
I don't have any thoughts or comments. This is great. This is what I had to bring, and I think the discussion has helped me at least see where you guys are at with this as well. I think the last thought that I would leave is keep your eyes out during the next couple of conferences, iClear, NeurIPS, etc., because I think this is going to be a huge catapult in or its own subfield as people start to investigate this with new conferences coming up.
Even if you get rejected, if you look on Open Review, I've seen a few CAN papers that get submitted and rejected for reasons like not doing big, large-scale analysis, not doing exactly the same stuff that I would complain about all the time, or they're like not pushing forward. So there are a couple of papers on Open Review already that have got reviewer feedback. People are trying, but I think reviewers are skeptical because every time someone makes a leap like this, you see that you need exceptional proof to make exceptional claims. So,
Alex had a question. Alex, go ahead.
Yeah, I wonder if we should try cans as just tokenizers because I sent a paper in the chat. They use higher wavelet transform for tokenizing the like the images and video.
Yeah, but HAR is like the simplest wavelet.
Yeah, but I'm surprised to see them like in tokenizer. I remember they use HAR features for face detection and traffic sign recognition. It's a Viola-Jones algorithm, and I think maybe we just need to kind of use wavelet transform or similar things just for tokenizing, and then applying transformer, for example.
that's interesting.
Was that library open singing? Yeah, I think you're mostly
different things.
you take computer vision class, the computer vision people still use that kind of stuff all the time. And they still, it's quite popular. Very few people are in that are like, I don't know. When I took my computer vision class, it was all classical methods. It's all like we did CNNs and one.
There's nothing wrong with classical methods, and there's no.
Yeah.
And OpenCV is comprehensive. That's why people use. Like sklearn, people still use learn. And why not? LaPac is from 1940s. Making it up, 60s probably. But yeah, thank you so much, TJ. That was a fantastic talk, and the memes in Slack and Network. Yeah, thanks.